let's continue with the this section on discriminants, and I'm gonna just finish off by giving you the a way of computing discriminants for number fields where the defining polynomial that you use is a particular nice form. This will be quite useful because it'll give us lots of examples of where we can easily compute discriminants. So this section is 2.2.23. So our subsection is called discriminants. Of trinomials. And we're going to start with just a small lemma. So this is lemma 2.24, which says the following. So let alpha be an algebraic number with minimal polynomial m alpha, and let beta be some element of this field q alpha, such that you have a relation between them. You can write alpha is the inverse of some linear combination of beta. So you have alpha equals a over b beta plus c, where a, b, c are just some rational numbers. Then what the lemma says, then it says that the minimal that the degree of m of alpha is the same thing as the degree of m of beta. Great. We'll use this. This is like a small technical lemma which we'll use later. So here's the proof. The proof isn't hard. So first consider, you know that m alpha of alpha is the same thing as m alpha of a over b beta plus c, and we know it's 0 because it's the minimal m alpha. Well, I should put the 0 over here. 0 equals this, because alpha is the root of the minimal polynomial of alpha. By clearing denominators, we see that beta satisfies some polynomial of degree m of alpha. If you just take this relation that we've written down, write out what the minimal polynomial of alpha is, substitute in this expression for it, and then now clear the denominators. You're going to get some expression, and you're going to get some powers of beta, and the highest power of beta is going to be the degree of the polynomial m alpha. So it's going to satisfy some polynomial of degree m alpha. Call it, say, f of x. Therefore, the minimal polynomial of beta has to divide f of x, because if it's minimal, so it'll divide any polynomial which has beta as a root. And this implies that the degree of m of beta has to be less than or equal than the degree of f of x, which we just said is the same thing as m of alpha, which equals the degree of m alpha. So we have the first, we have degree of m beta is less than the degree of m alpha, and now let's just do the converse. Now note that you can write beta is 1 over b a alpha inverse plus c. Just rearrange. The same argument shows, the same argument as did above shows that the degree of m alpha to the minus 1 here has to be less than the degree of m beta. So I've just reapplied this whole algorithm now, but in this setting with beta and this thing swapping around. And now there's an exercise that was in the lecture notes. So now by exercise 1.4.9, we know the degree of m alpha inverse is the same thing as the degree of m alpha. This exercise just asked you to, given the polynomial for m alpha, find the polynomial for m alpha inverse. And so we get the result. So we get degree of m alpha is less than or equal to degree of m beta, which implies combining the two things, you get the degree of m alpha equals the degree of m beta, star 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 plus star star, and this is the result. Okay, so this is just some fun dilemma, but it's just going to show up in a minute. So here's the theorem that I want to prove, which we'll use a lot. So theorem 2.2.25. So let K be some number field like this, be a number field with the minimal polynomial of your defining element of the following form, and it just looks like x to the n plus ax plus b. Then I'm going to give you a formula which gives you the discriminant of this this field. Well, discriminant of the power basis of this. So then the discriminant of the following basis, 1 alpha to the n minus 1, where n is the degree of this polynomial. This is minus 1 to the n minus 1 over 2 times n to the n b to the n minus 1, so in brackets plus minus 1 to the n minus 1, n minus 1 to the n minus 1, a to the n. Okay, so it's some horrible expression involving, well, has a's and b's, but here's some horrible expression. But now, for any field like that has minimal polynomial, any field where my generating element has some minimal polynomial like this, we'll now know the discriminant without having to calculate any matrices or anything like this. So this is why this is a useful theorem. So proof. So first thing is by proposition 2.2.19 that we saw last time, we have that the discriminant of this thing, this power basis, this is minus 1 to the n minus 1 over 2 times the norm from k to q of m prime of alpha evaluated at alpha. This is what this proposition was telling us. So now I'm going to let beta be whatever the number this is, m prime alpha of alpha. This is again some algebraic integer. Then we have, if you consider what this looks like, we have beta equals n alpha to the n minus 1 plus plus a. Just differentiated this minimal polynomial here, and then I plugged in alpha. So beta is this, which I can rewrite as minus n minus 1 a minus nb alpha to the minus 1. Since this rewriting is since we know that alpha to the n plus a alpha plus b equals 0. So using this I can rewrite this side of the equation. Okay, since this, maybe I should write a bit more details. Since this implies n alpha n minus 1 equals n a minus n b alpha to minus 1. Since this implies this, so which gives all of this together, it gives that alpha is the same thing as minus n b over beta plus n minus 1 a. I just rearrange my equality. Well, I rearrange this side of my equality. So now I have alpha being some ratio of beta, and these two polynomials, these two elements are of the form that we had in the previous lemma. So we can apply this. So Now, using, what was it, lemma 2.2.24, we see that n, which is the degree of m of alpha, equals the degree of m of beta. So we have these two things. Moreover, if we take, say, m alpha and evaluate at beta, which are, well, not at beta, at minus nb. So if you take the polynomial and now evaluate the middle polynomial and evaluate it at this expression. So on the one hand, we know that this is alpha, so this the thing is going to be 0. But if you take it and rearrange it, and we clear the denominators, so you just plug in this, basically plug in this into this thing. You know it's alpha, so you know it's going to be equal to 0, and then just rearrange and you're going to get an expression for beta. We get that. So what do you get? You get that beta plus n minus 1 a to the n minus na beta plus n minus 1 a to the n minus 1 plus minus n to the n b to the n minus 1 equals 0. This is what you get from just evaluating at this. Therefore, beta is a root of the following polynomial. Well, I'll just put x as in x plus n minus 1 a to the n plus minus na x plus n minus 1 a n minus 1 plus minus n to the n b to the n minus 1. So it's a root of this polynomial. So root of this polynomial, which is monic and has degree n. Therefore, this has to be the minimal polynomial. Has degree n, which equals the degree of what we know. We know that m. So we know that whatever the minimal polynomial of beta is, it has to have degree n. And here I've found a polynomial of the right degree, which is monic and beta satisfies. So this has to be the minimal polynomial. I don't have to check any other irreducibilities. Okay, so we know what the minimal polynomial of beta is. So now, by proposition 1.6.6 or corollary 1.6.8, whichever two you want, we have that the field polynomial is the same thing as the minimal polynomial of beta. We know this. Therefore, by proposition 1.7.3, we see that if you do minus 1 to the n times the constant coefficient of C beta, we get the norm k to q of beta. This is what this proposition tells you, that the constant coefficient has something to do with the norm, and once you fix the sign, then it's exactly what the norm is. So we get this is the constant coefficient of this thing, so we get n to the n b to the n minus 1 plus minus 1 to the n minus 1. This expression. So now we know what the norm of beta is. And now just plug it in to the previous result, and we get the result. So and then this, which gives the result. And we're done. Great. So yeah, it's not clear. This is what you get from the constant coefficient of all of this stuff once you plug it all in. So and remember, the beta was defined to be the derivative of the minimal polynomial of alpha divided by alpha, which is exactly the norm. Yeah, we needed to find the norm of beta because this is the term that we wanted to figure out. And by doing all of this rearranging and clever manipulation, we figured out what the norm of beta is. And so this gives us the result. So an immediate corollary of this just comes from for cubic field. So corollary 2.2.26. So we let K be Q alpha be a number field with M alpha. Go to the next line. M alpha of x equals x cubed plus ax plus b. So if you have cubic, then maybe you've seen this expression before. The discriminant 1 alpha alpha squared is going to be minus 27 b squared minus 4a cubed. If you've done elliptic curves, then you'll have seen this number show up. Great. So this basically solves all of our need to find discriminants for cubics, because if you have a cubic, any cubic, and say it had an x squared term, then you can just do a change of variables and you can replace it by some cubic which has no x squared term. So somehow you're completing the cube instead of completing the square. You complete the cube somehow, and then changing the variables isn't going to really change if you're a primitive element or not. And so you can take, if I give you a number field, say defined by some cubic and there's an x squared term in there, you can somehow rearrange it, get another cubic polynomial which has the right form, and then from that you can work through to get a discriminant. So let me just make a remark. So, well, this is in the notes. For any number field, well, for any poly of degree 3, we can make a change of variables so that it's in the form well, x cubed plus ax plus b. If you have a look in the notes, you'll see exactly what the change of variables that you need to do is. But let's do an example of how this corollary of this theorem works. So let alpha be a root of x cubed plus x plus 1, and k be the number field that it generates. Then immediately we don't have to do any calculations. We know that the discriminant of 1 alpha squared is going to be minus 31, which I'm going to note is square free. And therefore, by corollary, was it 2.2.9, we have that 1 alpha squared must be an integral basis. And we're done. We've figured out an integral basis here because we could, once we knew the discriminant of square free, we're done. But we didn't have to calculate the discriminant. You don't have to do any matrix or calculate any big determinants. This is pretty simple. And then, yeah. As an exercise, go ahead and try and do this for quadratics. And you'll be able to get a formula for quadratics. Okay, so this ends the section on discriminants. Next, we'll look at cyclotomic fields, which will be some special examples of number fields, which we'll care about more in the future. And then we'll move on to something else. So I'll stop here for now.